All right. Can you hear me?
Yes.
Okay. So, I have a bunch of Zoom stuff in my way here. All right. So, I guess, yeah, this is going to be a little bit more, kind of a loose walk through the theory of like why we need to keep rerunning VASP over and over and over again for every one of these time steps. Because basically we need to get particular information out of that wavecar file. So, probably want to know what's in the wavecar file. And if you look at the VASP wiki page, this is the information that is stored in it, but you're not going to be able to just open up this file and look at it because it's a binary file. So the only way to really read this data, since it was put into binary through Fortran, you're going to want to read it back out through Fortran as well. And that's why we use these Fortran scripts to do this. So really what we're after here are the wave functions. And by the way, if you're ever confused about like, something that VASP does or like, variables or whatever, I would highly recommend this wiki down here that has done me a lot of good a lot of times. And that's where, this picture is taken from. It's just the wavecar page on there. So yeah, why do we care about the wavecar files? They hold the wave functions and we need those. So the way that VASP usually runs is that it's trying to converge toward equilibrium. And in an equilibrium geometry, or like in the ground state, the wave functions are all orthogonal. And so effectively what that means is that we can't have any transitions from one state to another. And so the system isn't really going to do anything electronically speaking. So we don't really want that. So we need to get around that somehow. So we do our molecular dynamics run, right? And that means that all of our molecules are moving around and changing positions constantly. So if we look at, say like the 134th time step and the 135th time step, the nuclei will be in slightly different positions between those different snapshots. And that means that if we compare the orbitals from, say the 134th snapshot and the orbitals to the orbitals from the 135th snapshot, those orbitals are no longer orthogonal to each other because they'll be slightly shifted because of the change of the nuclear positions. So what that kind of means is that these orbitals will, sort of overlap each other just a little bit. And that little bit of overlap is what we need to get an electron to move from the one orbital to the other. So how do we actually utilize that? Sorry, trying to move Zoom stuff out of the way here so I can see what I'm looking at. So basically, we have these, big long integrals that we don't want to do, so we just have a supercomputer do them for us. So this Vij quantity, this is a measure of like how much these orbital I and orbital j are overlapping each other. So this is sort of a quote unquote simplified version of like the one that we actually do. So this is just saying that we're integrating over space. Don't really worry too much about that. This is the ith orbital from the first snapshot, and that depends on where we're looking and all the nuclear positions. This is the jth orbital from our second snapshot, just spatial coordinate again, and then positions of all of our ions. So if we shift one of those ions just a little bit between our time steps, that's going to alter our orbitals. And now that will make this integral, I guess, not equal to the Kronecker delta, right? It's not going to be 0, assuming that these are different, and it won't just necessarily be 1 if these are the same. We're going to start to kind of take, more or less continuous values here. Let me know if this kind of doesn't make any sense. So like in this case, right, like these wave functions, they depend on like all the positions of our nuclei. And so like here, we're just assuming that we'd move 1, right? And that's enough to change it. But in reality, that didn't work. There we go. All of our nuclear positions have probably changed. So this is basically the same thing as that last one, except instead of it being just this one thing that has changed, every nuclear position has probably changed now. But otherwise, this is the exact same thing. We're just looking at, the ith orbital from our first snapshot and the jth orbital from our second snapshot. And now these orbitals can kind of intermix a little bit. And this quantity is sort of how much like space they share. And so, so once we have that, now our electrons can transition from state to state, so we can do electron dynamics. And that's what we're interested usually when we're doing dynamical things. So my experience with this is, using red field theory. So this is the red field tensor. Don't worry too much about this. You got all these gamma things, blah, 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 blah. But like the V's are used to calculate these quantities. And so that winds up giving you this red field tensor, which the values more or less tell you how readily an electron will transition from like one state to another. It's something to that effect. And ultimately, we plug this into this thing down here, solve this whole equation, and that will wind up giving us the time-dependent electron density of our system. So this quantity here is really what we're after for electron dynamics. So this is telling us how the positions of the electrons are changing with time. And that can give us transition rates. There we go. So in order to calculate that sort of stuff, that's what we use the B script for. I just pulled the first one that I found. They all generally do the same thing, but they're going to look a little bit different depending on the details of like, which version of VASP are you using? Are you using like closed shell, or are you doing non-collinear spin? So you're going to have to probably dig around a little bit and find the right B script for what you're trying to do. But the general structure is that you're going to loop through all of your what am I trying to say? Like your snapshots of your nuclear positions, like all your different time steps. So that's what this whole for loop is doing. This might look kind of weird depending on if you've ever done like any shell coding. This is just formatting it so that basically the script will say P005 instead of P5, because that's the way that our files are organized. So that just makes stuff work. Excuse me. Oops. So this is just copying our wavecar file to a different file, because when we rerun VASP, it's going to overwrite the wavecar file. So we're ultimately going to be comparing this one to the wavecar file after VASP is run. And that will give us, our first time step, second time step. These P whatever files, these are really just postcar files at that particular moment of time. So before we run VASP, we want to make sure that we copy the appropriate postcar file like into what VASP will read as the postcar file. Otherwise, we're not going to have our nuclei in the right positions. You might want to take a look at these things before you get too carried away. This basically changes which style of VASP you're running. The ones that I'm aware of are this one, which is gamma, there's standard, which is STD, and then there's NCL, which is non-collinear. So if you're doing closed shell, you probably want to do either gamma or standard. But if you're doing anything, if you have spin up, spin down stuff separate, you're going to want to do VASP, NCL. I think gamma can do some of that too. I can't remember. It's been a while. But you're going to want to make sure that you check this as well, because this is telling you how many cores you're running your program on. And that needs to match up with your nodes that you assigned in your, it's not the SBash file, but it's the one that's got, # SBash, whatever, # SBash, whatever. Just make sure that you kind of look at like, either the Nice Landing, Haswell, whatever architecture, and make sure that this is appropriate. I don't think that you actually need to change that one. You start running stuff and it's going to start running other scripts. It's not always going to be the same scripts. That's something to kind of keep an eye on, because you might need to change which scripts it's running, because the directories might be different. I ran into all sorts of problems when I was doing this stuff, and I had to recode things. So it was just keep an eye on it, make sure that things are actually lining up correctly, and make sure that this file is actually in that directory. So like these ones will actually use the information from the wavecar files, but these are going to be Fortran scripts, so I don't know, you might have to look into those. Oops. And just make sure that those are working right if you're getting errors. And then ultimately, what we get out of this is these coupling files, and these contain this information here. So basically, you set it up to go between, all the orbitals that you're interested in, whatever that range was, and these coupling files will have all of that data inside of those. And then, gotta move my thing again. So the way that it actually gets calculated, there's a overlap.f script. There's actually a few of them, but they will have usually some function written inside of them, and this is sort of the function that starts to calculate non-adiabatic couplings, hence the NAC. If you've never used Fortran before, these things are just to indicate that you're doing a multi-line command, so that because it doesn't end with semicolons, it's just kind of it's an old school language. This is one way to comment. This is another way to comment. There's a bunch of other stuff too. If you ever have issues and have to recode stuff, feel free to ask me because I've had to do that before. But yeah, so this is you can find this one here in that particular file, and you've got all these different input variables here. Basically, this is your first one. This is the second one, right? First one, second one. If you see the DT, that basically means that that's your second snapshot. Oh, come on, there we go. This is just some more raw code from there. This is the end of what we were already looking at, and then this also calculates like non-adiabatic couplings is sort of the next step of that. And so this thing here is equivalent to this part of that equation that we were looking at. This part here is equivalent to this part of that equation that we were looking at. So this is sort of where the actual calculation happens right here. So yeah, you may wind up needing to kind of recode things a little bit. So just kind of useful to know where that stuff is. And this is, I guess, just kind of a broader view of that same thing again without all the stuff in the way. And I think that is everything. Yep.
Okay, please join me in thinking about it. And let's welcome Aaron, Dr. Aaron Ford, who joined us this meeting. So we have more and more visitors. Aaron, nice seeing you. Thank you for joining. So let's chase Landon and please him by questions, either from in person, or from online, or on chat line. Joseph?
I hold it pretty low.
Okay. Vanessa, do you wanted to chase your fellow physics major?
I guess I want to look at the slides later to follow it all, but at the moment I can't take the question.
Yeah. I kind of tried to write it so that you could, do that and look back at it. And this paper that I wrote, the way that I wrote up the methods section is, with the intent of it making sense to someone that was, at my spot in my career at that point, because I didn't really have a lot of resources that made much sense to me at that time. So I kind of tried to make it, upper level undergrad friendly. So hopefully, it makes sense on there if you need more, theory background behind it.
I had a question about that equation there.
This one or this one?
The first one.
Okay.
So everything right for the dr, is that also in the integral, or is that?
Oh yeah. Yeah. So basically, yeah.
Okay.
A lot of times you'll see in like complicated integrals, you'll see your d whatevers right away. And that way you just kind of declare like the thing that you're integrating over right out of the gate and everybody can kind of see it instead of, what you usually see in like math class or whatever, where you have the D whatever at the back.
Yeah.
But it's the same thing. It doesn't matter.
Yeah. Got it. Thank you.
There was a question from Lola in the chat line.
I am just opening that up right now.
So it's an unbiased question.
Okay, so Lola's question is, I'm not sure how I get the idea of the wave car and wave car old files because I know the wave car old file does not get saved. So I guess what I should say is that like, in these scripts, you're gonna wind up reading data in from the wavecar file and the wavecar old file. So the idea here is that we're dumping all of the wavecar data that we did have into a different file called wavecar old, and that way when we rerun BASP and it overwrites whatever file was called wavecar, we still have our old one around. So like this one would be our electronic states from say we're at like the 5th time step before we run BASP here, right? So this would be the electronic structure at the 5th time step, and then once we run BASP the next time, we'll have regular wavecar, which will be the electronic structure at the 6th wave step. Then we run these scripts, and we have our 2 adjacent time steps, and then we can do this sort of thing with it. And then the next time we go around, it'll get overwritten with the 6th time step, but then BASP will run, and then we'll have the 7th one. So that way we always have sort of the 2 that can piggyback off of each other, and we can always compare the orbitals of adjacent time steps.
Okay, thank you.
Dimitri is asking, what is the meaning of the curly brackets? I'm assuming these curly brackets. So this is just saying that this is the set of all of the nuclear positions at this time. So instead of writing it like this, which is a more explicit way of doing it, we just say like lump all those into this set. And then likewise, this is the set of all the nuclear positions at the time, t plus whatever our time step is. So the next time step. And Dimitri is asking me to clarify if I am teaching spinless or spin polarized versions of the codes. The one that I had pulled up is spin polarized. So essentially, this block is the exact same thing as this block, but this one is dumping stuff into, like this is for spin up things, and this is for spin down things, but these are doing the exact same thing. They're just putting them into different places, namely these up and down directories. So if you do a spin restricted one, you'll basically only have one of these blocks. It'll probably look a bit different because you're not going to use this exact script because this is spin polarized and you don't need that. But yeah, so this is kind of where you want to keep track of like which B script you're using, because if you use the wrong one, it's just going to error out. Nothing's going to work. And how is the overlap procedure programmed in Fortran? Is it possible to wash the lines of the code?
I think you did show it.
Yep. Yeah, that's this part right here. And then you could watch it if you want. You'd basically put like print line statements into this code, and then it would start spitting everything out onto your terminal. And that's useful for like debugging, making sure that things are reasonable. And then if if you bump into errors or whatever, you kind of see where it happens. Okay, and that is the end of the questions in the chat line. Does anyone else have any questions?
Oh, yes, there is one.
I do not see it. My chat thing disappeared on me now. Suppose it. There we go. So when reading the V sub ij in Fortran, is it truly an imaginary value, or is it assumed to be imaginary and has a real value? I guess I would have to dig into the code more, but yeah, because Fortran can handle complex numbers, so I don't know why we wouldn't be able to do that. Because once we have computed this integral, like this value should be imaginary and this value should be imaginary, but this value by the time we're done should be real. But there might be some tricks in the code that I would have to look at where maybe these are actually just kind of, real, but close enough to the actual value after we do all this that this is effectively the same.
There are tricks, and maybe Aaron wanted to give. Aaron, do you want to answer your question yourself, or you were just giving chance Landon to try?
I guess it's something I don't truly know myself, but I've been playing with the code, and it's something to keep in mind if you're trying to make sure your calculations are accurate, or what you're computing. Is the types of the variables.
Yeah. Well, because I saw that there were complex variables, but I was, just skimming through stuff pretty quick, so I wasn't really paying that much attention. But I know that the scripts do save at least something to complex variables.
Okay, I will give partial answer, maybe incomplete. So, how do we know which of the orbitals I or J should be evaluated at the incremented time? Should it be time increment for J or time increment for I? And if you're not sure, probably you should do both. So the one that you wrote, plus the one where you put dt into the I wave function and no dt into J wave function. And then you should average between them.
Yeah.
And when one does this trick, then imaginary, one makes rotation in complex plane one way, another does rotation in other way and direction, and when one makes an average, imaginary part disappears and Vij will be real.
Okay.
And
yeah, that makes sense to me. I guess that's clever. Yeah.
And the credit the author is to John Talley, who is likely retired now, and Sharon Thomas Schiffer, who is active now, and I don't know. She was jumping. She was invited from one top university to another one, like from Pittsburgh to Urbana-Champaign to Yale, and maybe she either at Yale or promoted even higher. But this symmetrization of adiabatic couplings was designed in 1995. Aaron, are you satisfied? Oh, okay. Let's check if you have more questions to Landon. One, questions two, questions three. Please join me and thank you, Landon, once again. So we have 3 more talks, which it last as short as 15 minutes or as long as another hour. Let's see. So next